In June 1997, the Near spacecraft, on its way to photograph the asteroid Eros, passed by an asteroid called Mathilde. Now, on its way, it reaches a distance of at least or of about 1200 kilometers, excuse me. So the distance between the two masses is 1200 kilometers. And at the time, the Near spacecraft was moving at a constant velocity of 10 kilometers per second. So let's say velocity equal to 10 kilometers per second. Also, the mass of the spacecraft, M1, is going to be 805 kilograms, and the size of Mathilde is 70 kilometers by 50 by 50 kilometers. To better illustrate what's happening, this diagram shows that the Near spacecraft, it was moving at a constant velocity in the positive x direction until about 1200 kilometers from the center of Mathilde. The spacecraft will, of course, experience some gravity or force of gravity because of the large size of Mathilde. Now, we know that because there is a force of gravity, the trajectory of the spacecraft is going to change by at least a small amount. So for part A, we're going to diagram just a rough diagram of what will happen to Near as a result of its encounter with the asteroid Mathilde. So we know that, so let's say Mathilde is right here. If the Near spacecraft was moving horizontal at a constant velocity, and as the problem dictates, at around 1200 kilometers from the asteroid, it will experience a force of gravity. Because of that force of gravity, what will happen in the coming time intervals is just an ever so slightly change in trajectory. So if the x-axis is this, it will be moving just under the x-axis. And that is only because of the net forces acting on the spacecraft. As of right now, the only force acting on the spacecraft should be the force of gravity, which is the gravitational constant times the mass of the spacecraft times the mass of the asteroid all over the distance between the two masses squared. Now, the net force is only going to be this force of gravity because it's in space, so we're going to neglect any other gravities from masses that are far away from the spacecraft in the universe. So and it's moving at a constant velocity, so there aren't any thrusters or of some sort on the space that are being used on the spacecraft. So the only force should be the force of gravity between these two masses. Okay, so for part B, we're supposed to calculate the change in momentum. To do this, we're gonna start from a fundamental theorem. Change in momentum over change in time is equal to F net. This is the momentum principle. And if we modify this a little bit, we get change in momentum equals F net times change in time. Now, to find the change in momentum, first we must figure out the net forces on the object being the spacecraft, and then the time interval we would want to do this for. First, figuring out F net is pretty simple. We know that there aren't any other forces acting on it other than the force of gravity. So F net should just be the force of gravity between the two masses, which should just equal negative g times m1 times m2 all over the distance between the two masses squared. But we run into a problem. We don't know what m2 is. We weren't given it. But we were given the size of the asteroid, which is 70 by 50 by 50 kilometers. And since we know that if we just multiply these three dimensions together, we'll get a volume that is the product of these three numbers multiplied together. And we know that the density of rocks on Earth is about 3,000 kilograms per meter cubed. Now, the formula for density is simply mass over volume. If you manipulate volume, we can find what mass is if we multiply density and volume together. The product of these numbers should equal about 5.25 times 10 to the 17 kilograms. Now that we know that the mass of the asteroid, the mass of the spacecraft, which is 805 kilograms, the distance between the two, which is 1,200 kilometers, and the gravitational constant, which is 6.7 times 10 to the negative 11, we can compute the F net, which will simply come out to be about negative 0.0197. Further background to this problem is that the astronomers, when they're recording or measuring the distance of near from Earth, they used radio signals, and radio waves, like light, move at about 3 times 10 to the negative 8 meters per second. And so their time measurements were as accurate as a nanosecond. So because of that, we're going to use the same time interval that they used, which is going to be 1 nanosecond, which is 1 times 10 to the negative 9 seconds. If we go back to our fundamental theorem or principle, we know that the change in momentum is just going to be F net times the change in time. And that should equal about the product of these two numbers should equal about negative 1.96 times 10 to the negative 11. So for part C, we're going to estimate how far off course the spacecraft would be after 1 day after encountering Mathilde. Now, straight up, we know that the change in time will be 60 seconds times 60 seconds in a minute, which is multiplied by 60 minutes in an hour. And that means that it will be 3,600 seconds in about 1 hour. And if you multiply that by 24, we're going to get 8,600 times 24 is going to be 8,600 or 86,400 seconds. And that will be our change in time. if we go back to our fundamental principle, we know that the change in momentum is equal to the net force times the change in time. And we've already calculated that the net force is equal to negative 0.0197. And I did this in vector form because to find the distance that the spacecraft went off course, we would need to use the y direction, because otherwise the only direction we were working with before is the x direction. And when we want to know the distance it changes, it will be only changing in the y direction, because earlier in our diagram the force only occurs at this point, which is straight downward, and that would be only in the y direction and not at all in the x direction. So if we go back to our fundamental theorem, we know that the final momentum is equal to the initial momentum plus F net times delta t. And we know that initial momentum is just the mass of the spacecraft times 10,000 kilometers per second in the x direction. This is our initial velocity. And so if we just calculate what this comes out to be in vector form, it's going to be m1 times 10,000 plus the force of gravity between the two masses, vector form, times the change in time, which is 86,400 seconds. Now, if we add these together, we get 8.05 times 10 to the 6 for in our x direction, the momentum in our x direction, and in the y direction we get 1702.08 in the negative y direction, and then the z direction will still remain 0. And from there we can compute what our final velocity will be if we just divide the momentum by the mass of the spacecraft, which is just 805. So this will go back to being 10,000 meters per second in the x direction, and this number will divided by 805 is going to be negative 2.11 meters per second in the negative y direction, and 0. Now that we know that what the velocity is, and since this would be a rough estimate, we're going to only use the final velocity as our average velocity, and we're going to also go to a derivation of the momentum principle, which would be just the change in distance is equal to the velocity times the change in time. And we know that the change in distance is going to be the final distance, or the final position, is equal to the initial position plus v, which is velocity, times the change in time, which is again going to be 86,400 seconds. Now, we need to know what this initial position is. And since the problem was unclear as to what that is, we're simply going to use the initial position as the origin as the initial position. Since we're only trying to find how far off course, we don't really need to find its position relative to anything. We just need to find the distance that it moved off course. So if we use the origin as our initial position, it will just be the final position equals velocity times delta t. Delta t is going to be 86,400 seconds, and our velocity is simply going to be 10,000 meters per second in the x direction and negative 2.11 in the y direction. So our final is going to be 864 million meters, and in the y direction it's going to be negative 182,682.872 meters. So since the impulse of the force of gravity was only in the y direction when it occurred, we only really need to focus on this number right here, since this would have happened anyway. Since in the original diagram, this was moving in the x direction at the same constant speed, and after a day it will move in the x direction in the same constant speed, because the net forces on the spacecraft did not affect it in the x direction. And also, if we just simply look at this number, we know that the spacecraft moved downwards in the y direction by a number of 182,682.872 meters. And that's how far off course the spacecraft was because of its encounter with Mathilde, and this was after a day. From accurate observations of the location of the spacecraft one day after encountering Mathilde, scientists concluded that the asteroid was just a loose arrangement of rocks with lots of empty space inside. What was it about their observations that must have led them to this conclusion? To determine what their observations were, we must look at this retrospectively. What they concluded was that Mathilde was a bunch of rocks with a lot of and the whole mass was just a bunch of empty space. And since there's a lot of empty space, that means the density is much lower than they had originally observed. And because of that, mass must have been much lower than they originally thought, because since density is equal to mass over volume, if density goes down, then mass has to go down as well, because they're proportional. And since mass is much lower, that means that the force of gravity between the two masses has to be much lower. And this goes back to the formula for it, where if the mass is much lower, then the proportional force should be much lower. And since the force is much lower, then the net force is much lower. And if the net force is much lower, then the change in momentum will be much lower. Therefore, the change in velocity will be much lower. And eventually, the change in position will be much lower. And if the change in position is much lower, then they must have concluded that the change in position was much lower than what they calculated. This, they must have found, they must have after a day figured out that the position was much closer to what its original position is. So if the x-axis were this, instead of what they thought would have been something like that, it was something much closer to the x-axis, which is the original trajectory of the spacecraft. So since they discovered that the spacecraft didn't change by much, that means the mass of the asteroid was much lower than they had originally assumed.